Thanks, Dinshaw, for very exciting talk and excellent simulations. I mean, it would have taken a long time, I guess, in supercomputers. Okay, so we are open for questions. So unfortunately, there are not many astrophysicists in our department, and so there's not many questions coming from them. But let me ask you a few questions.
Sure.
So for the sun, magnetic field is weak. That's why you're not seeing this effect. So what you're calculating?
Yes, that's right. And the sun, the other thing about the sun is that the sun has a very weak luminosity compared to a massive star. So so we're talking here in this talk, we were talking about stars that are about 25 solar masses or 40 solar masses. And the interesting thing about such massive stars is that they actually emit 1,000 to 10,000 times the luminosity of the sun. So if the sun were emitting 10,000 times its current luminosity, it too would go ahead and have a wind like this because of radiative effects. But the radiation pressure from the sun is very minuscule compared to that. So we don't get the radiatively driven winds. So for the sun, we actually have to resort to heating processes, magnetohydrodynamic heating processes in the base of the solar corona in order to set off the solar wind. So it's very different physics for starting the solar wind.
So in your simulations, you have, I mean, how big is your domain? So
it goes from the radius of the star to 15 times the radius of the star.
15 times. And you have
outflow boundary condition quasi steady state.
I see. And the boundary condition is outflow. I mean, things can flow out of the box.
Yeah, at the outer boundary, it is outflow. That's right.
Okay. And what are you solving, Dinshaw? I mean, these are MHD equations or
these are full compressible MHD in a rotating frame with mean magnetic field and fluctuating magnetic field.
So these are ionized stars.
Yes.
At the surface, okay.
Yeah. So basically, you can imagine the star as having a surface temperature of 20 to 40,000 degrees Kelvin. And when you have a star which is that hot, basically it's like saying that everything outside of the star is cooked, and everything, all the temperatures outside the star will basically temperature lock to the surface temperature of the star.
So regarding the dynamo part, so if you start with tiny magnetic field, do you think, so are you planning to do some work on that to amplify the magnetic field to reach a high magnetic field?
I think it's a very interesting. I think it's a very interesting problem. I know the technology is associated with doing that. The issue here is that we're using a fully compressible code. So the time steps are minuscule in this code compared to the time steps that you would need to take for a dynamo problem. So for a dynamo problem, it would actually require doing semi-implicit code formulation so that you can take much larger time steps. Because notice that for the solar wind to actually flow from the surface of the sun all the way out to its heliopause, takes only a few years. Compared to that, the solar dynamo cycle requires simulating over a long number of years. But yeah, Mahendra, if you're very interested in this problem, send me a couple of very good graduate students, and maybe over the next few years, we can solve this problem.
Very good, yeah.
Because there's a lot of important development. There's a lot of important code development that is needed. Even though we have the mesh and we have the technology, there's a lot of important code development that is needed before you can simulate the dynamo problem. But it would be a first class problem to solve.
Yes. Excellent. So any questions from the audience? So these are, you write in Fortran, if I recall correctly. I mean, so you're using
it's a combination of Fortran and C++.
Okay.
Whatever works.
Okay, great. So your mesh generation is your own, or you're using some other mesh generation?
I'm sorry?
Mesh. You're creating your own solver for mesh.
Yeah, we create our own mesh generation just to kind of keep it very simple.
Okay, great.
I see that Professor Ramchandran is there. I mean, he
Yes.
actually taught me he actually taught me the first physics 1 course that I took. I think it was mechanics. He and Kalyan Banerjee were there, right?
Okay, see. So, RR, would you like to comment? Would you like to just say, RR?
What fraction of the material that is thrown out by the star is hydrogen?
Okay, so these stars, they're basically still stars that are undergoing their main sequence lifetime, which basically means that they have hydrogen and helium and other metallic structures in the same ratio as our interstellar medium. So our interstellar medium also has about 80% by way of mass of hydrogen, 20% by way of mass of helium, and 20 or 19%, and about 1% by way of mass of other heavier elements.
I see. Okay. I was just curious because it is said that almost all heavy materials that we find on Earth is really cooked up in stars,
Yes.
various stars. But what gets thrown out for most stars is just simply still hydrogen and helium and light material, right?
Yes, that is true. But it's very interesting, and you're touching upon a very interesting topic, because what happens is that eventually these stars undergo a supernova. And what these stars do is that they are prodigious factories for cooking up higher, heavier elements. So hydrogen goes to hydrogen and helium, they basically interact, and eventually you get carbon, nitrogen, oxygen in this. And if the star is massive enough, you'll get silicon and iron also in its core. But when the star blows up eventually, it basically gives back all of these heavy elements back into the interstellar medium. So it's not the wind itself which is going to return heavy elements to the interstellar medium, but the end product when the star has given up its life is a supernova. And it's the supernova that will actually return all of the heavy elements that it has formed over its lifetime to the interstellar medium. And then other processes of churning up the interstellar medium take place, which make sure that these metals are kind of widely distributed into our galaxy. It's just like stirring up your coffee cup and making sure that the milk is uniformly distributed with the coffee. It's similar. Turbulent processes will actually mix up the material into our interstellar medium, and then from that we will have lower mass stars like our sun taking place, and then these lower mass stars are the ones that actually can sustain life. I mean, the stars that are like the ones that I talked about, they can their ultraviolet flux is so high that they would basically sterilize everything around themselves and make life impossible. So our sun is a very hospitable.
Nice to see you after so many years, and
yeah, it's wonderful. I'm happy that
we are able to meet in the cyberspace even these days.
Yeah.
Okay.
Thank you.
All right. So I guess we don't have any more questions, Dinshaw. So thanks for the talk again.
And thank you very much.
So I had a question.
Yeah. Yes, Singta, please go ahead. Yes.
So when like the stars you were talking about, you said that they are much more larger than the sun. So when they go supernova, so like our sun is not expected to like go into a compact object like neutron star or a black hole, but they like do these large stars which you talk about have a possibility of collapsing into a compact object?
Yes, these large stars will eventually, we think, either collapse into a neutron star, or they might eventually go ahead and form a black hole. But our sun also, at the end state of its life, is a white dwarf. So I remember the first time I was introduced to white dwarfs was in StatMech course that I took at IIT Kanpur, where they actually went ahead and worked out the degeneracy pressure of a electron gas, and then showed exactly how it allows you to sustain a star with a certain amount of mass. So white dwarf stars are in fact expected to be the end state of our stars like our sun. And those are degenerate stars too.
So, sir, like as Professor Ramakrishna, like earlier we were talking about that the heavier metals. So when it collapses into a compact object, does the heavier objects, like the heavier metals which were made in the stars core, do they like burst out, or are they like stay inside the compact object? Or
They were,
Get
stars do a fantastic dance before they actually give up their lives. And so less massive stars like our sun will actually go ahead and form a gigantic envelope at some point. And then that envelope blows off, and what remains behind is a white dwarf. But more massive stars will actually go ahead and blow off a significant fraction of their mass, we think. And eventually, when all the nucleosynthetic processes in the center of the star run out, namely when you form iron, you can carry out no further nuclear reactions. Because in order to carry out these nuclear reactions, you actually have to release energy. Okay, and iron is the most stable object, stable element, in the sense that you cannot burn iron and get more energy out of it. So once these stars reach the point where they have an iron core, a silicon iron core, then they can produce no further energy. And once they reach the point where they can produce no further energy, they cannot keep staying on the main sequence, and they have to kind of go ahead and go supernova at that point.
okay, sir. Thank you.
Sure.
Okay, great. Any other question? So that's very nice explanation, Dinshaw. Good. Great. Okay, so we'll end now, and hopefully we'll invite you in person to Kanpur. And
Thank you very much.
more
Very kind of you.